So here's some notes on the notion of direct sum. So if U1 up to UM are subspaces of some vector space V, we say V is a direct sum of these subspaces if each V in V can be written uniquely in the form V equals U1 plus U2 and so on up to UM, with each UI in the corresponding subspace. So what exactly do we mean by uniquely here? Well, one answer is that if V is U plus O plus W, direct sum W for some V in V, and we have some particular choice of decomposition, V equals U plus W, then if we choose some other U prime, which is not equal to U, there's no solution, there's no partner W prime, such that V is equal to U prime plus W prime. So for example, think about a blackboard or a piece of paper. We have two vectors, U and W, and we can think about the subspace W, big W, which is multiples of little w, and the subspace U, which is multiples of little u. And every vector on the whole space can be written as a sum of some one of those, something which is multiple of u plus something which is a multiple of w. Now, if you play with it for a second, you can probably convince yourself that these are the only choice of little u and little w that would work to write v. If I chose some other u prime, which was not equal to w, say u prime is 3/2 w, then the w prime I would need in the dotted line here, such that v is equal to u prime plus w prime, has the wrong angle, so it's not in the space w of multiples of little w, and so there is no solution. One thing to note here is that there's no requirement that w and u are perpendicular. In fact, there isn't even a notion of perpendicularity available, but we'll get to that later in the class. Nevertheless, it can still be true that v is the direct sum of these two pieces. Now, unless for some reason v is some tiny finite set, checking whether v is equal to a direct sum by looking if every vector in v, every single vector in v has a unique decomposition, of course, is not going to be feasible. It's an impossible thing to do. So what we want is some kind of a test or a criterion, some kind of shortcut that lets us figure out when that's possible, when v is equal to the direct sum. So here's that shortcut. It's we call it the direct sum criterion. It's proposition 1.44 in your book. So suppose I have some subspaces u1 up to um of my vector space v. V is equal to their direct sum if and only if two things are whole. Well, first of all, I have to be able to write every vector in v as a sum of things, one in each subspace. And secondly, instead of uniqueness, it's enough to check that 0 has a unique representation. That is the only way to write 0 as a sum, u1 up to um, with each little ui in big ui, is if all the ui's are already 0. So that's a really handy criterion because that's a much simpler thing to check. So we can specialize this to the case of two subspaces. So if I have two subspaces, u and w of v, v is equal to the direct sum of u and w if and only if two things hold. First of all, v is equal to u plus w. Everything in v can be written as a sum of something in u plus a sum of something in w. And secondly, the intersection of u and w is 0. To prove that, suppose v is the direct sum of u and w. By definition, v is equal to u plus w, so the second part of the criterion 2 holds. And if we consider some v, which is in u intersect w, well, then since u intersect w is a subspace, minus v is also in u intersect w, and I can write 0 trivially as v plus minus v. In particular, as the intersection of u and v is in u, and the intersection is also in w, v is in u, and negative v is in w. So 0 equals v plus minus v is a perfectly good decomposition of 0 into something in u and something in w. But by uniqueness of the representation of 0, we already know that 0 equals 0 plus 0, we must have that this v is itself 0. On the other hand, suppose that we have already that v is the equal to 0, u plus w, and the intersection of u and w is equal to 0. And consider some expression for 0. 0 equals u plus w, with u and w and w. We can add the additive inverse by the additive inverse property. W has an additive inverse. It lies in v, so we can add the additive inverse of w to each side, minus w, to get that minus w is equal to little u. And since little w is in w, so is minus w. Then this equality here means that u, little u, is in fact in w, so little u is in the intersection of u and w, but we assumed that the intersection of u and w was 0 to begin with, so little u must be the 0 vector, and similarly w is equal to the 0 vector.